What we are going to talk about today is linearity and superposition. Now, in most classical first electrical engineering textbooks, you only learn about what's called the superposition principle. But the superposition principle is part of a larger concept known as linearity that will get referenced a lot in this class. So I take the time to actually explain what that means to you, partly because I don't like to talk about things and have to say you'll learn about it later because I think that it's a BS excuse. And another reason that I like to talk about it is because it can be used as a very powerful circuit tool itself if you know what you're doing. To understand the concept of linearity, though, we have to take a look at our circuits from a very different perspective. For those of you in electrical engineering, you'll literally take an entirely separate couple of classes on this concept, linear systems and signals and digital signal processing. For those of you that are in biomedical engineering, all of that will get lumped into one single class that you should take, I think, in your sophomore year, maybe earlier junior year. And for the rest of you, it may pop up, it may not, I'm not super sure. I think mechanical engineers learn about it, but I'm not sure about chemical and a couple other guys. And that perspective that we're going to utilize here for a little bit is the concept of looking at a circuit from a system level. So instead of looking at a circuit and saying, all right, we have voltages and currents and this, that, or the other, we're going to look at it from, if we apply a particular input signal, which could be a voltage or a current, what are the outputs that we are getting, which could also be a voltage or current. So from a system perspective, we might be able to represent a circuit like this. So we have a linear, and I'm going to talk about what that means, black box network. Excuse me. And this linear black box network, what the heck just happened? Could have multiple input signals. And so I'm going to call my input signals X's. So we might have some function x1 of t that's applied at the input. And that input x1 of t will generate an output y1 of t. We could apply a different input x2 of t and get a different output y2 of t. And the way for us to test whether or not this system is a linear network is to determine if the additivity property is maintained and the homogeneity property is maintained, and I'll talk about those two things. But that litmus test is effectively this large mathematical expression, which I know for a fact none of you are going to understand, but it'll be okay. So we could say that H of alpha x1 of t plus beta x2 of t needs to equal alpha y1 of t plus beta y2 of t, or in a more shorthand notation, we could say that h of x of t needs to equal y of t, where h of x is what's called the transfer function of our system. So let's talk about what this mathematical statement is trying to say, okay? So H represents how our system acts on our inputs to produce our outputs, right? So it's more commonly called a transfer function, all right? So the first part of our expression, H acting on that alpha blah, 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 is just saying how the system acts on our inputs. Now, alpha multiplied by x1 of t is just a scaled version of that input signal. And beta multiplied by x2 of t just means that we've scaled that second input by a different amount than we scaled the first input. Okay? So what we're saying here then is that if our system acts on a scaled version of input 1 and a scaled version of input 2, and produces an output that is simply the sum of the scaled version of output 1 plus the scaled version of output 2, we have a linear system. I know that seems weird, but it's actually a very, very powerful state. Okay? It can be broken down into two discrete properties, the first of which is the additivity property. So the additivity property says if several independent inputs are used to excite the system, the total response where response is just a fancy math word for output, to all of these excitations can be determined by considering each input separately while assuming all others to be 0. So at a system level, what that means is that if we have our black box network with a transfer function h of x, if we apply an input x1 of t and observe an output y1 of t, and we take the exact same network apply an input x2 of t, observe an output y2 of t, then we could take that network and apply an input x1 plus x2, so just the sum of the input signals, if it's obeying the principle of additivity, our output should just be y1 and y2, or the sum of y1 and y2, which are just the outputs due to the input signals acting alone. Okay. This, in a circuits class, is more commonly known as the principle of superposition. The superposition principle states that we can analyze a circuit by leaving only one input signal on. Could be a voltage source, could be a current source, doesn't really matter. Analyze the circuit, and then reanalyze the circuit with all of the other inputs on exactly once. And if we add the results of all of those analyses together, we will get the exact same answer as if we had analyzed the circuit with all of the sources on at the same time. So I would like to prove that to you. So that was too fast. We'll go to a new page. It'll be okay. So let's say that we have the following circuit. We have a 6-volt source, a 6-ohm resistor, a 10-ohm resistor, a 9-ohm resistor, a 2-amp source. And our quantity of interest that we are trying to solve this circuit for is this current IX flowing down through the 10-ohm resistor. We are going to analyze this circuit in two different ways. Our first method of analysis will be to have both of our sources on at the same time. And we're just going to use whatever we can to solve for this quantity, I sub x. Our second method of analysis will be to use the additivity or superposition principle and analyze the circuit with only one source on at a time, add the results together, and see if they match our prior analysis. Okay? If they do, then we can easily say that this circuit containing voltage source, current source, and resistors is a circuit that obeys at a minimum the superposition principle or the additivity principle. Okay? So method number one, I'm going to call it normal analysis. So for us right now, normal analysis means the application of Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. So what I'm going to do is I'm going to assign voltages to all of our elements that don't currently have a voltage, or at least all of our resistors that don't currently have a voltage. And I'm going to assign currents as well, and we're just going to try to throw the kitchen sink at this problem until an answer falls out. Okay. So I want to call the voltage drop across my 6-ohm resistor V6, and I'm arbitrarily choosing the positive polarity terminal to be on the left. I'm going to call the voltage drop over my 10-ohm resistor to be V10, arbitrarily putting the positive polarity terminal on top. And I'm going to call the voltage drop across my 9-ohm resistor V9, positive polarity terminal on the right. And I chose the positive polarity terminal on the right purely because there's a current of 2 amps flowing into that positive polarity terminal. So I just figured, well, I get to know what that one is pretty easy. I can also call the current flowing through my 6 ohm resistor I6. And so this is not the only way to solve this problem by any stretch of the imagination, but it just happens to be the way that I'm going to do it. If I apply Kirchhoff's voltage law around the left-hand loop, what I get is negative 6 volts plus V6 plus V10 is equal to 0. Everybody okay with that? I can use Ohm's law and express V6 as just 6 times I6. So that's going to be 6 ohms times I6 plus 10 ohms times IX is equal to positive 6 volts. And I'm going to call that equation 1. Is everybody okay with that? Just using Ohm's law to rewrite those voltages in terms of those currents. And now I'm going to apply Kirchhoff's current law at top middle node. And what I have is a current of I6 flowing in. I have a current of 2 amps flowing in. And I have a current of IX flowing out. And so I can rearrange this guy and say that I6 minus IX is equal to negative 2 amps. That's my second equation. So again, all I'm doing there is applying Kirchhoff's current law at the top node, the one on the top in the middle, and just saying the current flowing in, which is I6 and 2 amps, equals the current flowing out, which is IX. I now have a system, 2 equations, 2 unknowns. You guys all have calculators. Take a moment to solve that system for me, please. So when I solve the system, I find that I6 is negative 7/8 of an amp and IX is positive 9/8 of an amp. Did anybody else get a similar result? All right, so that's method 1. While it's pretty easy and straightforward for me to do that, how many of you would have thought of applying KCL and KVL and setting up a system of equations? Probably not many of you, right? So I would argue that a circuit this, I don't want to call it trivial, but it doesn't have particularly a whole heck of a lot of elements or anything like that. It's not too huge, but a circuit like this isn't beyond what you're able to do, but it would challenge you at this point. Okay. Not wildly rough or anything like that, but it'd take you a little bit to do. Okay. Now let's analyze the circuit using method 2. Superposition. All right. So superposition is actually going to require us to analyze the circuit twice because there are two sources in the circuit. So there are two excitation functions, all right? So our first go will be with the voltage source on and the current source off, all right? So I'm just going to redraw my circuit. Leave my voltage source on. And this is everything but the current source, right? So let's talk about what it means to turn a current source off. Sully, do you have any guess as to what that means? So if I have a 2 amp current source, how much current would the source supply if I turned it off? None. That's what it means to turn a current source off. It should supply 0 amps of current. So I'm going to turn a current source off in a circuit by replacing it with an open circuit. Because for an open circuit, I know exactly 0 amps of current can flow through it. I'm going to call this current Ix prime because it represents what's going on in the circuit with only one of the sources on, okay? So let me ask you guys, how would we go about solving for that quantity Ix prime where our current source has been turned off? Faith, do you have any ideas? Exactly right. So if there's an open circuit on the right-hand side, effectively all of the current, whatever it is just going to flow around this path. Right? It's going to flow through the 6 ohm resistor, then it's going to flow through the 10 ohm resistor, then it's going to go back up through our voltage source, and it's just going to circulate around and around and around. We know that none of it can branch off and flow through the 9 ohm resistor because the 9 ohm resistor isn't part of a closed current carrying path. So how do we quantify it mathematically? Anybody? All right. So using Ohm's law, where V is equal to IR, that means that I is equal to V over R. So that would just be 6 volts divided by the total resistance seen, which is 6 ohms plus 10 ohms. So that's going to be 6 over 16 or 3/8 of an amp. Anybody have any problem with that level of analysis? All right. We'll analyze the circuit again with our voltage source off and our current source on. So if we turned a voltage source off, excuse me, a current source off by replacing it with an open circuit, which forces the amount of current flowing through that branch to be 0, how do you guys think we should turn a voltage source off? No, a short circuit, right? And for an open circuit, the current is fixed to be 0 and the voltage can be whatever it needs to be. For a short circuit, the voltage is fixed to be 0 and the current can be whatever it needs to be. So we're going to turn off voltage sources by replacing them with short circuits or wires. So this wire represents my voltage source turned off. Then I have my 6 ohm resistor, my 10 ohm resistor through which I'm going to have a current flowing IX double prime. And this is the circuit that I need to analyze now. So, building on what we did last lecture, I know that there is a current of 2 amps that is entering the network that contains the 6 ohm resistor in parallel with the 10 ohm resistor. So this is a perfect opportunity for me to practice my current division and find IX double prime directly. So I can say that IX double prime is going to be 2 amps multiplied by, sorry, it's being weird, 1/10 over 1/10 plus 1/6, which, let's see, so 1/10 is 3/30, and 1/6 is 5/30, right? So that's going to be 5 over 8. No, sorry, 3 over 8 times 2 is 6/8 of an amp. By all means, put it in your calculator and don't do it mentally like I did. When you confirm that result, if this circuit is obeying the additivity or superposition principle, IX, which represents the current through that 10 ohm resistor with both sources on, should simply be IX prime, the current flowing through the resistor with just the voltage source on, plus IX double prime, which is the current flowing through the resistor with just the current source on. So if we add these results, 3/8 and 6/8, we get 9/8 of an amp, which is exactly what we got analyzing the circuit with both sources on. I would argue that while we do have to analyze the circuit twice in this case to use superposition, the analysis that we have to do is a lot easier than what we had to do with both sources on at the same time. So this is pretty powerful by itself. Bradley, did you have a question?
I wanted to ask, how is there a way you'd be able to know we can use superposition to solve a problem without doing the first one?
Absolutely. So the way to know whether or not you can do superposition is, does the circuit contain only linear circuit elements? So linear circuit elements are resistors, capacitors, and inductors. So every circuit that we are going to analyze in this class will be a linear circuit. Okay. Yeah, so this is always a valid means by which to solve a problem. Okay. So we have proven to this point that a circuit containing a voltage source, some resistors, and a current source at a minimum obeys the principle of superposition, or the additivity portion of linearity as a whole. So the next thing that we're going to talk about is what's called the homogeneity property. This one isn't as obviously useful, but situationally, it's pretty fantastic, right? So before we analyze, or before we go into the homogeneity property, I'm going to build a little table here, and I'm going to kind of carry it with me because we're going to check things, all right? So my table is going to have inputs and outputs. And so on the input side, when we first worked it, the problem, we had a 6-volt input and a 2-amp input. And we observed that our output was 9/8 of an amp. That was the result of method 1, right? Then we analyzed the circuit with the 6-volt source by itself. We saw that the output was 3/8 of an amp. We analyzed the circuit with the 2-amp source on by itself, and we observed that our output was 6/8 of an amp. Okay, so you guys, I know you've already started writing it. You honestly don't need to keep track of this. This is just for me proving things to you. Okay. So let's now talk about the homogeneity property. Or scaling. So the homogeneity property says that if an independent input is used to excite a system, scaling that input by an arbitrary factor of alpha causes the output to scale by the same amount. So if we have a black box system with a transfer function h of x, we apply an input x1 of t and observe an output y1 of t. If we take that same black box network and apply an input of alpha x1 of t, then we should observe an output of alpha y1 of t if this system obeys the scaling property. So effectively, if my system obeys the scaling property, if I double my input, my output should double. If I half my input, my output should half. So let's prove that by analyzing the circuit that we did a moment ago. But we scale both of the inputs by a factor. So let's say that now our circuit is this guy. So we took the 6-volt source and we doubled it. We're going to relieve the resistors alone. And because I'm sorry, I should double that 2 amps to 4 amps, my apologies. Because we're not quite ready to deal with both scaling and superposition at the same time, we're going to have to analyze this guy in the same way that we analyzed the circuit in method 1, with both sources on at the same time. Okay. So I'm going to call this voltage V6, this current I6, this voltage V10, and I think those are all of the pieces of information that I used. My KVL equation is going to be 6 ohms times I6 plus 10 ohms times IX is equal to 12 volts. My KCL equation is going to be I6 minus IX is equal to -4 amps. So this is the result of me taking the equations that I developed earlier and just doubling the contribution of each source. I don't really need to go through the full analysis steps again. It's going to work the same way, except the sources are going to be twice as large, right? That's what I did. So if we throw this guy into our equation solver, we'll get values for I6 and IX again. And the expectation here is that our values will double because we doubled the inputs, all right? And so what I get is -7/4 of an amp for I6 and positive 9/4 of an amp for IX, which is exactly twice what we observed earlier. So let me paste my table here. And add these data points. So when we put in twice 6 volts plus 2 amps, our output was 9/4, which is exactly twice 9/8. So this system obviously then obeys the scaling property as well, okay, because it satisfied the relationship. So the last question that we have to answer here, which will prove whether or not this circuit is linear, is if it obeys the additivity property and the homogeneity property simultaneously. And so what I mean by that is I can scale individual inputs by separate factors, and I can apply both inputs at the same time and get the exact same result as if I had analyzed the circuit using superposition while scaling those inputs. And so I'm going to make a prediction here, all right? So I'm going to scale the voltage source by a factor of -3. So I'm going to have -3 times 6 volts, right? Or a voltage of -18 volts. What should my expected output with just that voltage source on be? So when I had 6 volts, my output was 3/8 of an amp. Right, so if I scale my input by a factor of -3, I should scale my output by a factor of -3. And so I can take that -3 times 3/8. So I should get -9/8 of an amp. Okay. And let's say that I scale my current source by a factor of 5. That should scale the output of the current source on by itself by a factor of 5. Sorry, I forgot my unit there. I apologize. So that should look like 5 times 6 is positive 30 over 8. So what I expect to happen is that when I apply a scaling factor of -3 to my voltage and a scaling factor of positive 5 to my current, my output should just be the sum of those two numbers, which is positive 21 over 8, right? If this system is linear, that is what the answer for Ix will be. So let's see whether or not that's true. If it is, then our system is linear. Okay. So if we have an 18-volt source with this polarity, sorry, this should be a 6 ohm resistor. This is a 9 ohm resistor and a 2 amp source. Excuse me, this shouldn't be a 2 amp source, it should be a 10 amp source because I've scaled it by a factor of 5. If I analyze this circuit, I should expect to see that my output is 20, or my value for I sub X is 21 over 8. So I will have 18, sorry, let me. I'll have 18 plus 6 ohms I6 plus 10 ohms IX is equal to 0, which means 6 I6 plus 10 IX is equal to negative 18 volts. When I apply Kirchhoff's current law, I get IX plus 10 amps is equal to, sorry, I6 plus 10 amps, my apologies, is equal to IX, which I can rearrange and find I6 minus IX is equal to negative 10 amps. And solving this system, I will get values for I6 and IX. I'm going to throw this into my calculator. Negative 18 goes there. Negative 10 goes here. I get negative 59 over 8 amps for I6 and positive 21 over 8 amps for IX. So my prediction worked perfectly. I was able to scale the inputs individually, so not everything by the same factor, and was still able to predict how this circuit would behave. Therefore, it must be a linear circuit. What this means is that I could actually work a circuit with one source on at a time and make every source 1 volt or 1 amp, and then scale it by whatever it needs to be to match what you're asked. And you can solve circuits that way if you were insane enough to do so. That would probably be very, very long and tedious way of doing things, but you could do it. In your homework assignment, you were asked to work the following problem, which is rather annoying. So this is homework number 5, problem 2. This is a perfect example of where the principle of homogeneity in particular can be used and abused to simplify analysis. Okay. So in this problem, you have an unknown voltage source, Vs. And then you have a resistor network where we have a 2 ohm resistor, 4 ohm resistor, six ohm resistor, an 8 ohm resistor, and a 10 ohm resistor. And we want the current Ix, which is the current flowing through the 10 ohm resistor. Part A says if Ix has some value, so let's call it 250 milliamps, solve for the value of Vs. And part B says if Vs has a value, call it 66 volts, solve Ix. Effectively, you're being asked to solve this circuit twice. We can solve it once and use that homogeneity principle to get the answer to the part we don't want to solve. So I'm going to ask you guys, and we'll work this together. Would you rather solve the circuit knowing what Vs is and trying to determine Ix, or would you rather solve it the other way around, where we know what Ix is and work to solve for Vs? Somebody pick. Pardon? The first one, where we know what Ix is and we're trying to find Vs. Okay. So if Ix is 250 milliamps, we now have enough information to figure out what the voltage drop over the 10 ohm resistor is, because we know the current flowing through it and the resistor value itself. So what is the voltage drop over the 10 ohm resistor? Right, so if Ix is 250 milliamps, hit me with a number, Norman. 0.25 times 10 is 2.5. Since the 10 ohm resistor and the 8 ohm resistor are in parallel, that means the voltage drop over the 8 ohm resistor is also 2.5 volts. Everybody okay with that? That gives me enough information to solve for the current flowing through the 8 ohm resistor. So what should that be? McKinley, got any thoughts? Pardon? That is incorrect. So we have a 2.5 volt drop over an 8 ohm resistor. So it's 2.5 volts divided by 8 ohms is 312.5 milliamps, I believe. Right, 2.5 over 8. All right. So now that we know the current flowing through the 8 ohm resistor and the current Ix flowing through the 10 ohm resistor, we know the current flowing through the 6 ohm resistor using Kirchhoff's current law, right? So that's just going to be that 312.5 milliamps plus that 250 milliamps, or 562.5 milliamps. And that gives us enough information to determine the voltage drop over the 6 ohm resistor. So we take that 562.5 milliamps, multiply it by 6 ohms, and find that we have a voltage drop of 3.375 volts over the 6 ohm resistor. Everybody catching what I'm throwing? You want me to slow down or re-explain things? I'm happy to do it. So what we could do now is use Kirchhoff's voltage law and figure out what the voltage drop over the 4 ohm resistor is going to be, right? Because it has to be the voltage drop over the 6 ohm resistor plus the voltage drop over the 8 ohm resistor for this particular polarity, right? So that's going to be 3.375 plus a voltage drop of 2.5 volts. Looks like 5.875. We can now use that value to find the current flowing through the 4 ohm resistor, which this is getting ugly, 1.4685 amps. And we can use Kirchhoff's current law. Find the current flowing through the 2 ohm resistor. That's just going to be that 1.46875 plus 562.5 milliamps, giving me a total current of 2.03125 amps, which means the voltage drop over the 2 ohm resistor is 4.0625 volts. And from this, Vs is 4.0625 volts plus 5.875 volts, or 9.9375. That analysis had nothing to do with superposition or anything that we did today. Honestly, I was hoping that you would pick option B, where we could just get to practice voltage division a couple of times, but you didn't, and that's okay. All right. So this was the long and tedious part. All right. It was part A, so I would understand why most of you would gravitate to doing that first. You were asked to do it first, but it's the harder of the two means by which to solve this circuit. So how do we get the answer to part B by doing no circuit analysis whatsoever? Well, 66 volts is just a scaled version of that 9.9375 volts, right? Which means 250 milliamps scaled by that same factor will give us our output IX for a known value of Vs. So we know how the circuit behaves. We effectively have the transfer function. Now we just need to scale the output by the same amount that the input has been scaled. So our scaling factor, alpha, in this case, is just 66 volts divided by 9.9375 volts. Or 6.6415, and then some other bits. And from this, IX, when Vs is equal to 66 volts, is just alpha times 250 milliamps 1.6604 amps. No circuit analysis required. We already did all the circuit analysis by figuring out effectively the transfer function of the system, so we don't need to rework it again. Okay. Now, how I might give you a problem similar to this on an exam would be like a word problem that says you have a particular circuit and an input of 6 volts causes an output of 3 amps, and an input of 2 amps causes an output of -1 amp. Tell me what the total output would be if the input voltage were 10 volts and the input current was 3 amps or something like that. So I just give you a scaled version. Effectively, I give you the parts of what goes into the table, and then you just do simple manipulation to tell me what happens at the output.